Okay, in this item we have a two-span beam, but it has cantilever segments here. We've got a uniformly distributed load all the way along the length. We have constant EI along the entire length. So really we only have to look at one half of this beam. And so let's say we're going to take a look at the left-hand beam, and then we can reduce further that model by getting rid of that little cantilever, leaving us the statically equivalent model that is still indeterminate down here below. We're asked to find the appropriate values for M and P to use in this reduced model, and of course that's just going to be given to us by simple statically determinate models here, that if we're going to let B be the left support, C be the right support, then let's call that cantilever point A, and we've got then the distributed load going out there. Here's just to the left of B, and we'll have then our shear value and our bending moment value, and the shear value is easy, it's just equal to WL times that length is only L over 3, so WL over 3 is going to be that value, and then that's going to have a moment arm of L over 6, so that'd be WL over 3 times L over 6, or WL squared over 18. So from an absolute value standpoint, then we've got the values here for our equivalent static model. Right? And then we're asked to talk a little bit about what to do with all this. Right? So discuss the appropriate values of M and P to use. Okay, we did that. The appropriate equilibrium equations to be used, and if provided the results of the slope deflection analysis of the reduced model. They want us to use slope deflection to do all of this. Okay. Discuss how one then determines the rotation and transverse displacement at the end of the cantilevers out here, such as at A, since they're no longer going to be included. Right? In the slope deflection model that we've got here, then we only have one kinematic degree of freedom, and that would be theta B. Right? And what we would be doing then in that approach would be to go and say, well, alright, theta C is equal to 0, psi BC, that's equal to 0, so only theta B is the unknown, and we'd come along, there's our kinematic degree of freedom, we would write our slope deflection equation for each and every member in moment, so MBC would be equal to 4ek theta B, there is no theta C term, plus a fixed end moment, BC, and there's no chord rotation term. That would be the equation. We weren't asked to have to write that out, but it is instructive to be thinking in that regard. And we would go then to joint B, and the pertinent equation that would matter is, let's see, we've got this moment that has been applied from the cantilever, that's WL squared over 18, and then we got to get the MBC in here. Now sometimes I get a little confused in sign convention, so I come along and I'll write what's going on with the member itself, and we have chosen all along to use clockwise positive, so that on the joint positive would be counterclockwise. And so the appropriate equilibrium equation is that MBC plus WL squared over 18 is equal to 0. So there's yet another one of our answers. Of course, that will result in that MBC is equal to minus WL squared over 18. And when we substitute in to here, right, or rather the other way around, take MBC equation, slope deflection equation, drop it in. At fixed end moment BC is going to be a minus WL squared over 12, but we're not asked to find numbers here. But we would solve that for theta B. Right, so substitute in and solve for theta B. Right, now that we have that, note what else we're being asked to do. If provided the results of the slope deflection analysis of the reduced model, that's what we just did, discuss how we then determine the rotation and transverse displacement out here at A. So what we've got is, in the original system, is we got some sort of deflected shape, again sort of 0 slope here at the midpoint at our line of symmetry. And just only draw stuff on the left hand side. Come down with, then eventually we'll get some positive curvature going on here, and then we might get some more negative curvature going on here. And we'd get something that looks like that. Okay? Maybe. So let's look at this again from this perspective here. Let's draw this out. We got the frowny face portion, and we've got then the smiley face portion, and then a little bit of negative coming from that cantilever effect. Right, but there's going to be a non-zero rotation there for theta b. I anticipate that theta b will be positive, or it will be in a clockwise fashion, because the cantilever is only L over 3, and we got a lot more effect going on in the middle. We can do the math and see if that turns out to be the case or not. But the big picture here is going to be, if that's my undisplaced position of the beam, and here's B, if I come along and say I've got a then rotation that happens at B, let me then drag that tangent out. And so what's going to happen is here, then the real curvature that's going to end up is going to be the cantilever curvature that is superposed on top of then the curvatures that are happening, rotations that are happening from the middle. So this part out here would be theta b times L over 3, and then the tangential deviation would be this part, and be of A with respect to B. And so delta A, just being this little part here, is going to be the difference between those two, or the additive. We don't really know until we go and find out if theta b really is clockwise or not. But theta b L over 3 plus or minus then tangential deviation of A with respect to B. Now we could get these through moment area methods if we wanted to, or we could just also superpose the slope deflection theta b effect, which is this theta b L over 3 plus the cantilever displacements. Right, so we can superpose this portion here plus whatever happens from then the rotation and the displacement that happens down there at this one. So we're going to add those two effects together, right? And that's what's really happening here, that this is going to be your TA with respect to B. That's from a statically determinate system. And then when we want to go get the rotation at A, that's going to be the rotation at B plus or minus that theta A with respect to B. That's going to come from, well, that's kind of ugly in the way that got drawn. Let's get the tangent a little bit more carefully in here. But there's your theta at A with respect to the tangent drawn back here at B. And so we'll superpose those two effects all together ultimately. Again, either use beam tables, the cantilever displacements, or you can use moment area method to get all of those.